This is Mark Anderson for Keller Community College, section 7.4, confidence intervals for variances and standard deviation. All right, here. We're going to be taking a look at something new called the chi-squared distribution. And first, what's probably best to get to the why of this here. Why should we look at confidence intervals of variance and standard deviation? Because back in Chapter 7, we learned about finding confidence intervals of average and not the variance and not the standard deviations. So why should we look at these confidence intervals for these two things? Well, it's really because the variances and the standard deviations I'm going to abbreviate that, standard deviations, can be very important. So if you're making PVC pipes and your pipes have a very large standard deviation and we find that the confidence interval between your pipes are too big, then the pipes won't fit together. Drug dosage is extremely important because if the standard deviation inside of that drug, if we find the confidence interval is too big, then you're going to have some patients who get misdiagnosed. They're going to take the wrong dosage. They're going to get sick. So we do want to say, according to the data that we find, let's focus on that standard deviation and figure out if, even though the average might be beautifully into where we need it to be, that standard deviation may not be where we need it to be safe. So we're going to learn something called the chi-square distribution. It's given with this kind of cool x, but that x is pronounced chi, or in chi if you write it out, and these are called chi-squared distributions because most of the time you'll be squaring the answer. Now, this chi-squared distribution is a family of curves based on the degrees of freedom, and with a very, if you have a very small sample size, your graph is going to be extremely skewed to the right. Now, that's if you have a very small amount of sample size, but as you get more and more, as your sample size gets bigger and bigger, up to about 100, you're going to get these families of curves that's going to look more and more symmetric. So by the time you get to 100, you're going to have a pretty symmetric curve there. But since we're dealing mostly with very small sample sizes, we have this skewed right curve. And be sure to know that this, as a review from our first chapter here, this is called skewed right, our first test that we took. So this is a skewed right graph, and what we're going to be doing is we're going to take a look at the alpha I give you, and the alpha is going to be, this is going to be, how accurate we want this to be, and these are going to be two-tailed tests. So you're going to have two confidence intervals, one here, and this is going to be not symmetric. So normally when we have a two-tailed test, we have, a plus or minus critical value. But in this case, these areas under the curve are not going to be the same. These are going to be two different areas under the curve, and this is going to be known as chi-squared left, and this is going to be known as chi-squared right. And since this is a two-tailed test, we need to take our alpha and divide it by 2 for each of these tails. Because if we have an alpha of, hypothetically, let's just say the alpha is 90%, or I'm sorry, the alpha is 0.10, so this would represent, excuse me, 90%, then this would have to be 5% and 5%. So our alpha in this problem would be 0.10. So just make sure that when you're given the alpha, you cut the alpha in half for the tails. And I notice I'd put down 0.5. I should put down 0.05. Sorry for that little mistake there. 0.05. And that way you have 5%, 90%, and 5%. So this area in the middle here is 1 minus alpha, and the areas on the ends are the alpha divided by 2. All right, let's move on here. All right, scroll this down. Now, the table for chi-squared distribution is going to be on table G, and table G is on page 787. And make sure you divide your alpha by 2. Now, the chi-squared left and the chi-squared right, we're going to do an example of finding that 90% confidence interval when n is equal to 25. So let me do a little scratch work paper here. The alpha is 0.10 since we want a 90% confidence interval. Alpha divided by 2 is 0.05, and our degrees of freedom is 24, because we're going to go n minus 1 for this chart. Now, our chi-squared left, we're going to look at 0.95, and our chi-squared right is going to be 0.05. Now this is backwards to what you're normally doing. Usually you would consider the right side to be, or the left side to be 0.05 and the right side to be 0.95. But if you go look at your chart on page 787, you'll notice that that graph, or that picture there, has the area shaded to the right. Normally with our Z tables and T tables, tables E and F, our graph was shaded to the left. And as we figure out in the next section that we'll do, section 11.1, right-tailed tests are going to be the norm since chi-squared will always be positive. So the right and the left have opposite numbers that you're used to dealing with. So normally we consider the right side to be 0.95 and the left side to be 0.05, but that's not the case in this. So go look at the row of 24 and scroll across till you get to 0.95. And there you get your chi-squared left side of the table of 13.848. That's the area under the curve. That right now this number doesn't have a lot of context, but we will be using it in the next formula to find our confidence interval. And our chi-squared right is going to be 36.1415. Now again, these numbers don't have a lot of context just by themselves, but when you put them into the problem that we'll do in the next page or two, you will see where we have that. Now I want you to pause the video and try to do this one by yourself. Find chi-squared left and chi-squared right for a 95% confidence interval when n is equal to 11. Alright, hopefully you've given that a try. You've paused the video, and now I can write down my scratch work. The alpha is going to be 5%, so our alpha divided by 2 is going to be 0.025, which means my degrees of freedom, according to my sample size of 11, is going to be 10. Now, we're going to look at, for the left part, we're going to look at 0.975, and I'll just kind of keep that under the left part. And the right part's going to be 0.025 right there. Alright, so chi-squared left. Chi-squared left is going to be 3.247, and chi-squared right, according to our 10 degrees of freedom, is going to be 20.483. So there's our chi-squared left and chi-squared right. Now we will be using these in the next formula on the second page. Alright, so let's go use our knowledge of how to find chi-squared left and chi-squared right to find the confidence interval for variance and standard deviation. Alright, let's go take a look here. Alright, well here's the formula for confidence interval for variance and standard deviation. The formula is going to be to take n minus 1, which is our sample size minus 1, and then multiply that by the standard deviation squared, that would be the variance, and divide that by chi-squared right. And that will be our left bound for our variance, or standard deviation squared. And then we'll take our n minus 1, our sample size, multiply that by the standard deviation squared, or the variance, and then divide that by chi-squared left. Now it is a little bit sad that the chi-squared left and chi-squared rights are on opposite sides. You would, kind of hope that left would be on left and right would be on right. But this is the bigger number, and this will make our lower bound. This is the smaller number. This will make our upper bound. Now all of this finds this square of the standard deviation, which is called the variance. But to get some meaning out of this, what we're going to do is take our answers here and take the square root of the left side and the right side, and if we take the square root of that formula, what we then get is the standard deviation. And that confidence interval for the standard deviation will let us know if we have a pretty reliable number, or something within our specifications that'll be good for us. So what we're going to do is find the 95% confidence interval for the variance of the standard deviation of nicotine content of cigarettes if a sample of 20 cigarettes had a standard deviation of 1.6 milligrams. So let's put down what we know. We know our alpha is, and this would be a good time to maybe pause the video if you want to try to figure out the alpha divided by 2, the degrees of freedom, what our standard deviation is. So these are all little pieces that we'll need to kind of start the problem here. So you can pause the video and unpause it for me to reveal this. Our alpha is 0.05. Our alpha divided by 2 is 0.025, or 2.5%. Degrees of freedom will be 19 because of 20 minus 1. And then our standard deviation was given in the problem, which is kind of nice, is 1.6. So now we have everything but our chi-squared left and our chi-squared right. And this would be another place where you might want to pause the video so you can take a look and see if you can get those correct table values. Alright, to find chi-squared left, you'd have to look at 0.975, and to get chi-squared right, you have to look at 0.025. Chi-squared left is going to be 8.907, and chi-squared right is going to be 32.852. So what this gives you now is all the pieces you need for the formula. N minus 1 is 19 times our standard deviation, 1.6 squared, divided by chi-squared right, which is 32.857, which is going to be less than the standard deviation squared, which is variance. 19 times, that should be times, it looks like a decimal there, 19 times 1.6 squared divided by 8.907. Alright, so I'm going to work on this here, and this is going to give me 1.5, which is less than the standard deviation squared, which is less than 5.5. Alright, I'm going to take the square root of this whole thing, and by taking the square root, I get my standard deviation. So I'm going to show you this is 1.5, which is less than the square root of the variance, which will give me standard deviation, which will be less than the square root of 5.5. So this tells me my standard deviation of those cigarettes is going to be between 1.2 and 2.3. So what does this all mean? I just did all of this work and I got this for my final standard deviation answer, and this is my final variance answer. So what does it mean? Well, it means that we're 95% sure that the standard deviation of the cigarettes, I'll abbreviate this, I'll just put cigs here for cigarettes. The standard deviation of the cigarettes is between 1.2 and 2.3. Now, if your customers can notice that difference in nicotine, you might want to tighten up your group, because that sample size right there, if that's just too much variation, you're going to need to go back to the business and see if you can tighten that up. Alright, let's go scroll this down for our second of 3 examples. Now these examples are also in the book, which might provide just some different explanation there if you want to go and get it. But you'll notice that in this problem, we need to find our alpha. Wow, sometimes I do that there and make the little box instead of using the free draw here. Alpha, we're going to have to find our alpha divided by 2. We're going to have to find our degrees of freedom. And in this case, we're also going to have to find our standard deviation. Now you'll notice that the standard deviation right here on this, they don't give it to you. They give you the alpha. They give you the alpha divided. You can then find alpha divided by 2 in degrees of freedom. But notice that, we're not given the standard deviation. And that's where we go to our good friend, the graphing calculator. By going to our friend, the graphing calculator, and let me kind of put it up on the screen here. We can find that by typing all this data into our lists. Now, I've done so already, and in fact, I want to show you how we can do that. We hit Stat Enter, and that gives you, and that's where you can type in your data. And to get the standard deviation, we're going to go Stat, Right, 1, Enter. And there it is. Our standard deviation is going to be 5.3. So I'm going to move that off to the side here so I can use that. And I'll get back to drawing on the screen here. And hopefully you can pause the video here and find your alpha. Alpha divided by 2, degrees of freedom, and your standard deviation. Then you should go and check out your chi-squared left and your chi-squared left or right values for the confidence intervals. So why don't you pause the video here, try to see as far as you can go, and unpause the video to see if we sync up. Alright, our alpha is 10%. Our alpha divided by 2 is 5%. Our degrees of freedom is going to be 9 because we have 10 data points here. See, n is equal to 10, so there's our 10 data points. And our standard deviation is here at 5.3. Alright, I'm going to round it to 5.3, going one beyond the decimals here. Alright, so our chi-squared left, according to 9 degrees of freedom, at a 0.95 on the top of the chart, that's going to give me 16.919. And this is on table G. If you're still not getting the right answers here, just make sure you look at that. Oh, crap! I just put that in the wrong place. That was my right value, 16.919. And this is going to be 3.325. So for many of you who paused the video there and quickly scrambled to the book, sorry about that. And this is going to be 0.05. All right, so here's what we're going to do here. We are now going to type everything into our little formula here. N minus 1 times the standard deviation squared, 5.3 squared, over our chi-squared right, which is 16.919. That was my mistake. I looked here and wrote that here by accident. And this is going to be my standard deviation squared, or variance, is less than 9 times 5.3 squared divided by 3.325. Alrighty. So now what I'm going to do is I'm going to find variance by computing this out, which gives me 14.9. And this gives me 76.0. And this is my variance. Now what I'm going to do is I'm going to go and take the square root of all this. So, I mean, I can invisibly envision a square root doing all of these separately in square roots. So this is going to be 3.86, which is less than the standard deviation, which is less than 8.72. So the standard deviation of this problem is going to be between 3.86 and 8.72. We can be 90% confident of that. So the question that I covered up at the calculator, what does this mean? We are 90% sure that the standard deviation of the lift ticket sales is between $3.86 and $8.72. In the context of the problem, we were looking at lift ticket sales, and yes, you can find the average lift ticket sales, but you may want to bring maybe an extra $10 bill because the standard deviation, or roughly 66.8% or 68%, is going to be between $3.86 and $8.72. So bringing an extra $10 is probably a pretty good idea. All right, last problem here. Now the last problem is going to be another calculator problem. So what you're going to want to do is maybe pause the video and see if you can get this standard deviation into your calculator and replicate what I did. So pause the video and try to do that yourself, because when you unpause it, I'm going to have the answer up here on the screen. Okay, so what I've done is I've actually typed in the data into list 4. So I'm going to go second 4 and bloop. There's my data from this set. This is home ownership from randomly selected states. So now I'm going to go stat right 1 enter or stat right enter enter, and I get my standard deviation of 4.4. And I think I'm going to go one more than that because I'm going to go 4.45 because we had one decimal in our problem, so we'll go one beyond that. All right. Now, hopefully you found your standard deviation of 4.45, and again, that's good rounding right there. We have our sample size of 8 as well, which you could have counted on the page here. So you may want to pause your video and try to find your alpha divided by 2, degrees of freedom, and then your standard deviation, and your chi-squared left, and chi-squared right. So when you unpause the video, I will go through the problem. But try this one by yourself first. All right. We're looking for a 99% confidence interval, so this is pretty particular. So this is going to be a 1% alpha. That means my alpha divided by 2 is only 0.5%. Degrees of freedom, well, there's 8 items, excuse me. There's 8 items, so therefore our degrees of freedom are going to be 7, and our standard deviation was 4.45. That's rounded correctly. Now our chi-squared left, based on 7 degrees of freedom, is going to be not much, 0.989, and chi-squared right is going to be 20.7 or 278. And now we get to apply our formula. 7 times 4.45 squared divided by 20.278, which is less than the standard deviation squared, and then 7 times 4.45 squared again, divided by 0.989. Now, by crunching all these numbers, we're going to find out our variance is between 6.84 and 140.16. Now, taking the square root of everything, we get our standard deviation is between 2.62 and 11.84. So, in terms of the home ownerships of these states, we can come up with an average of these home ownerships. I mean, this average is going to be 69. But we can roughly say with a 99% accuracy that the standard deviation is going to be anywhere between 3 and 12. So that's a pretty wide standard deviation right there. So being 99% sure means that we're going to have a wider or a pretty wide range just to account for all the errors and inaccuracies. So we're 99% sure that the standard deviation of these home owners here is between roughly 3% or 2.62% and 11.84% or 12%. All right, if you have any questions, send me an email.